Hello, everyone. Thank you for joining Andrew Wesly Engineering. I'm Andrew Wesly, and today we're going to go into the Hex Counter, how the Hex Counter works and how it's implemented on the Altera DE2 development board. The Hex Counter is posted in the description below. So let's take a look at this. Let's go into the Open Up Quarters 2 editor here, and let's look at this. We're using the Cyclone 2 EP2C35F672C6 FPGA. And we're using the Hex Counter entity here on the top. So let's look at this file. It has inputs clock, reset, go, kill, and outputs are done, count output, that output our binary number using LEDs, and then we have our outputs for our 7-segment displays. I'm going to show you what that is. So these are our 7-segment displays, and we have an output that goes to them from the FPGA. So here are the port definitions. We have our inputs, clock, reset, go, kill, and then we have our outputs, done, count output, 7-segment output 1, 7-segment output 2 for our 2 7-segment displays. Then we have a register that holds our count, a register that verifies, that shows when the count is done, and then we have a state register to implement our state machine. We have 4 state machine parameters. We have idle, active, finish, and abort. So we'll use these signals to control our state machine that helps us control our counting. So here we'll instantiate our lower level modules, the 7-segment decoders. So these 7-segment decoders take as input a binary number from the FPGA and convert them into the correct signals that are displayed for the 7-segment displays. These things. These are the 7-segment displays. Let's take a look at this decoder entity. So a 7-segment decoder has inputs a clock, reset, and a 4-bit number, 4-bit binary number. And the output will be a signal that drives the 7-segment displays. So what we're doing here is we'll have our clock as our input, our reset as the input, and we'll have the binary number as an input, and then we'll have our output to our 7-segment displays here. And we'll have a register as an output buffer. So we'll have state machine parameters. So the overall design of this entity is to have as input the binary number and then a case, a selection that will select the correct state machine to drive the 7-segment displays. So we have 0 all the way up to 15. So that's 0 through F because we're using hexadecimal numbers. Here's our design implementation. We'll have our stimulus, a clock, and a reset, and we begin our state machine here. So case in 1, that's our input signal, and based on the case, we'll select these binary numbers. And it looks like when we're not doing anything, we'll output 0. When there's nothing, we'll have an output of 0. But we can see here, this is our mapping from 0 through F. 15 is F. And this is our output to drive the signals. Logical low is high. 0 is logical high. So that's our 7-segment decoder entity. And we're instantiating that here in our design. Let's take a look at our state machine. We have a stimulus, the clock, and the reset signal. If we get a reset signal, then we'll go to idle. Otherwise, we'll use our state register as our case. If we're in the idle state and we receive a go, then we'll go into the active state. If we're active, if we get a kill signal, then we'll go into the abort state. Otherwise, if we're in finish, if this is what count is at, if the count is this value, then we'll go to the finish state. After the finish state, we'll go to idle, as you can see here. If we're in abort, if we're with no kill, then we'll go to idle. And the default case is idle. So here we'll implement the counter itself. If we're in the reset state, we'll set count to 0 number if we get a reset. If state is in the finish, or if it's aborting, if we're aborting our count, we'll set count to 0 again. Now if the state is in the active state, if our state machine's in the active state, then we'll increment our counter. And that's it for the counter state machine. Then we'll implement a done register to show when we're done. We'll have a stimulus as clock, and reset. If we get the reset signal, then we'll set done to 0. If we're in the finished state, then we'll set done to 1. That indicates that we're done. Otherwise, done gets the signal 0 because we're not finished. And we'll take our counter value and assign it to our count output. That's how this program works. There's a state machine with 2 entities. Let's take a look at our pin assignment. So I've taken care of this before for us. I've assigned the device as the EP2C35F672C6 series. It's a Cyclone 2 FPGA available from Altera on the Terasic DE2 development board. And I've also taken care of the pin assignments. What this does is it maps the FPGA pins to the appropriate entities on the board. So we have a clock, pin N25, that's one of the switches. And you can see that in operation in the video that I have in the description, that I've linked in the description. This is the outputs mapped to the LEDs, done mapped to another LED. Then we have go, kill, and reset. Those are all mapped to switches. And then these are the signals that map to our 7-segment displays. So if you like what you see, subscribe. Hit the subscribe button and hit the notification button. And please, questions, comments in the video about this video below. I aim to put some more videos up here explaining about FPGAs, and I aim to have more projects up here in the link. So please hit the subscribe button and hit notifications. Thank you.